Okay, so thank you very much. My name is Okada, and I come from the University of Tokyo JSK Lab. Okay, okay, so
今、東大では世界最先端の研究開発が続々と生まれている。
sorry. Okay, and this is a video of our laboratories, and maybe some of you already saw this video many times in Bremen. I already showed this video in the beginning of my talk, and I think this is exactly humanoid robots in everyday activities. So today I discuss about the technology behind this video and also why we came up with this, we start this type of the human robot of everyday activity projects. So first, how we reach into the life-size humanoid. I talk about some history of our laboratory and also the history of the humanoid robotics researches. So this is some timeline of the JSK laboratory. It is one laboratory in University of Tokyo, and it's originally founded by professor in Norway around 1980s. So we have a very long histories. And it's so, but we are not started as a humanoid robotics laboratories. So this is a left side is a Professor Inoue's PhD work in 1969. So it's about 50 years ago. At that time, they only have one manipulator and the tactile sensor on the grippers. So the title of PhD is Computer Controlled Bilateral Manipulator. And I heard that at that time, the word robot is not used in the PhD thesis or research papers because it is considered as some scientific fiction sound. So this is why Computer Controlled Manipulator is the title of his thesis. And in 1983, Professor Masayuki Inaba, he is currently the professor at JSK as me, together with me. He built the robot that can manipulate the ropes. So this is the first time in our JSK laboratory to use the vision systems, because if you want to manipulate some object, especially for the deformable object or object in the environment, the vision processing is essentially important. So at that time, we are very interested in the integrated system of the vision and manipulations, but we are not the humanoid robotics researchers. And so who started the humanoid robot researches? So this video shows some history of the humanoid robots. And it says it started in the Waseda University. It is also in the Tokyo, Japan, around the 1973. So you see some two robots there. Left one is a robot, is a walking robot. And the right one is a piano playing robot. Maybe we need a sound for this. So this is very nice videos because there is an expo in Tsukuba around 1984, and they built this robot for that event. And yeah, this is very nice. And during the 80s, Honda also built the robot. And I think the robot from Honda is very famous. So in the middle, you see some Honda robot walking. And in 80s, they secretly started the humanoid robot project after they looked at the Waseda's project. And they built the robot and debuted in 1996 is the left one. And 2000, they introduced the Asimo. And the Asimo has the 3 generations because the shape of the Asimo is exactly the same, but they are changing the versions. So left one, the middle one is the original Asimo, which only walking like this. It is very famous Asimo style walking, I think. And right one is a newer version. It has completely different hardware, but they try to keep the, how can I say, image or brand of the Asimo. They build the robot as almost as exactly looking as original one, but the motors and computers are completely different. And this ASIMO can running and hopping. And in the 2000, Sony also developed the Sony small robot. It is a 60 centimeter and 17 centimeter size robot, and it is almost commercialized. So left one is they. I think they created this movie. No, right one. Yeah, right one. I think they created this film for the commercial when they start selling. But in 2002, the CEO of the Sony is changed from Japanese to Americans, and he did not understand the importance of human robots in as a business. So he stops all the project, and we never see this robot in the commercial or market. And of course, I think everyone now knows the Boston Dynamics. They are very good at human robot. You see a lot of this video in the YouTubes and also TV shows. So, but overall, I think the history of the human robots is more like the control problems. So, research of the human robot see this robot as a target of their, applying their control theory or dynamic control theory into the robot. So, the history of human robot in JSK laboratory is slightly different. So Professor Inaba started the remote brain robot 1993. It is much earlier than Sony's project. He thinks that robot as a whole body manipulations. So instead of controlling, instead of seeing the robot as a target of control dynamically or keep balancing, he more interesting in the whole bodies, like whole body motions or whole body manipulations, like swinging. And also, what we did in the 1993 or 1994, this is a walking robot, but instead of try to build the perfect controller for balancing or walking, we were more interested in how robot can get up or wake up after he is falling down. So this type of the motion is much more important for us. And also because of this robot is very small, and we just use a small servo motor used for the radio control car, each student builds their own robot. So each student builds their own robot and try to think about what this robot should do. So this diagram shows the research started in the knuckle walk or biped walk, but after that, students think like, okay, let's human robot to carry the object, or sitting in the chair, or swinging, of course, or using some tools like a motorbike, or carry the object by two robots. And also, interesting part is we did this research in one laboratories. So we want to, how can I say, design the research strategies, because in the university, students usually come up and go out every 3 years or 5 years. They didn't stay in the one laboratory for a long time. But we want to continue we have to continue researches. So in order to do that, we are more interested in the develop the software, which is independent from the robot body or robot motions. So we build one software, but each student builds different bodies. And the software must be abstract to the, how can I say, component of the body or the structure of the body. And also that software should have to be applied to different kind of the whole body motions. And this is what I did in the, while I was a student. I also was a student of the Professor Inaba, so I built my own robot using the 2 stereo cameras. And I also interested in the integrating everything from the perception and motion planning and actions. So this is very simple example that robot look at the environment and build the maps and find the path from the starting point to the goal and execute the actions. And we did that in the simulators, and which must be transparent to the real robot. So this is what I did during my PhD, which is we call it integrated software environment that combines both simulator and real robot and the packages for the robots and the computers like this. So after building these small robot systems, student and I try to apply this small robot system to to find the new application of the robot. So here is some examples like I don't know if you understand, but okay. So in the middle top shows the robot that how can I say holds the cup noodles, and then after the 3 minutes, the robot tells you, okay, it's done. Or this one show is a kind of the tour guided tour robot. So because I think the advantage of small robot is you can bring the robot to everywhere. So you bring the robot in the, for example, in the car, then the robot could be left ones. In the car, robot could be the navigators, and also they can bring the robot to the reception. Then robot tell you that if you have a booking or other things. Oh, so this is a video. Okay. So, and in our laboratory, in parallel with the small robot project, we also had a human-sized robot. And this is, in the beginning, it is also the student interested in the dynamic control of the robot. So you see that H5 robot in 1997, this robot is meant to apply the dynamic control systems like what we call auto balancer to this robot. And at that time, the robot is this is only one robot in our laboratory, and it is just built by students. So look at the people around the robot. They are very, how can I say, seriously watching the robot. And the student is, holding his hand on top of the run stops. So if something happens, he pushes the button immediately. But this is 1997 is very important because this is 1 year after the Honda rebuilt their robot P2. So it takes about 1 year for us to build this robot. And after 2 or 3 years, we built the robot named H7 or H7s as an integrated robot that combines the motions and arms and 3D vision systems. And you can see that the right video shows that exactly the same demonstration that I did with the small robots. So this is two main lines in the JSQ laboratory about the humanoid robot researches. And at that time, the professor Inoue, who started the humanoid robot project as a national project of Japan. And in the beginning, the left one, he started the project with a Honda P3 robot, and he thinks that the robot should be applied to many jobs, like using this kind of machines or carrying some heavy object with a robot or something. And because of this is a national project, it is very important to how the outcome of the project can be, how can I say, influenced to the research community. And because Honda P3 is very confidential technology, and at that time, maybe Honda did not want other people, except Honda people, to use this robot, this METI project is a government project. We asked the one company named Kawada to build the robot as a research platform. So, so left top one is HRP2 prototype. This is exactly same idea that we did in small robots, that robot can falling down, and after that he waking up from that postures. And so the downside, it's video in the bottom is HRP2. This is for the commercial version, and this robot is now in the market, and the researcher can buy this robot. So this is a first experience that we, after the HRP2 robot coming to JSK. So Professor Inoue really like this video because everyone around the robot, the student, is smiling because this robot is a platform, and because if you build your own robot, I think you understand that you always, how can I say, worried about if it is really working or it's, sometimes stops the programs or something. But here, none of them is actually, build the robot. They just use this robot, and they completely trust on this technology developed in the government project and also the Kawada company. So they are really happy about seeing robot is working. And also important thing is this robot comes with a fundamental software, including the working controller. So you don't have to do research on the dynamic balancing or controller. Instead, you concentrate on the manipulation or perception parts. So this is how I started the daily assistive tasks project using this HRP2 robot from the 2002, which is just after I graduated the university. So this is good timing for me because once you graduate or once you write the PhD thesis, you better to have a new project. And I have a new robot just after my graduation, so it's very good timing for me to move to the small robot to a large robot. And if I compare to the small robot with a large robot, the large robot is good advantage. Life-size robot is good advantage because it is very easy to find the new application, new motion, new behavior of the robot because everything around you is a good environment, a good object, good tools, good activities that should be, manipulated by, or that should be done by humanoid robot. So, for example, everyone here is sitting in chair, but I think it is still difficult for the humanoid robot to sit in the chair, and so it is your everyday activity could be the source of your idea to have a new project or new, research topics. So this robot is, how can I say, source of the ideas. And I also use the same software that I used in the small robot. So at that time, again, we have one software, and student has different robot, but the software must be, how can I say, transparent or abstract to the structure of the body or behaviors. And here we have one robot and the one bodies, but each student has a different type of the manipulations, the behaviors. And the software, we try to build the software that should be transparent or abstract to the different type of the behaviors. So this is how we are interested in the knowledge representation for the humanoid everyday activities. And this graph shows some idea of what's inside of the robot. So we have so this is 10 years ago almost. So at that time, we write everything as a knowledge into the systems. So we let robot to know the shape of the object and how, the color histograms of the object, and also where the robot should stand for each manipulations and where the object is likely to be located. So this type of the knowledge can be integrated in our systems. And okay, so this is a list of the knowledges. And I think the interesting part of our system is written by Lisp again. But this is not common Lisp. It is originally developed by researchers at AIST. And the unique part of this language is that geometric modeling system is integrated in the Lisp systems. So that means, for example, if you look at the MATLAB languages, you can use a vector or matrix as a first-class object in that languages. And here, we can use the 3D shape can be used as a first-class languages. So you can modify or add or use the 3D shape model as an object. And in this way, we build everything in the one languages. So everything means a robot and environment and object. And it also has the capability of adding some symbolic informations. So this is how we build the knowledge representation systems in the slide I showed in before. So this is not the images. This is exactly what our language understand. And this is, how can I say, if you have a Python language, if you print some object, you see the inside of the object. And this is exactly the same things for our languages. If we print object, then we have a viewer that show this type of what the languages understand or language contains. And okay. So this is how we generate the whole motions in the use Lisp system. So left side is what we see in the videos. A robot is opening this complex shaped object, wash dishes like this. But inside here, we have a 3D model of the environment and robot. And we just I can say program the robot by moving the joint of the object. And after we move the joint of the object, like doors, then we can understand how the handle of the object is moving. And we apply the inverse kinematics to generate this motion and translate it to the real robot. So the video I show in the beginning of this talk, this is how robot sees the world. So left side is a real world, and right side is a real world, and left side is what the belief state. And this is exactly programmed as in the Lisp systems. And the robot believes that robot is in front of the kitchen, and you see that right top, green line shows the 3D lines extracted from the belief state, and blue line is a result of the image processing. And by comparing these two information, robot knows that if the belief state is correct or not. And if it is not correct, robot should move or robot update the belief state. So this is how robot opens the water tap. And because robot has a belief state of the position of the I can say waters, so see that okay, so this is water flow can be detected or not. And once robot detects the water flow, then robot continues the next motions. So here robot sees the hand of the human and recognize the dishes and then update the belief state. So again, I think the power of having the knowledge-based system integrated in the computer languages, you can use that system for the motion generation, and at that same time, robot uses that system for the recognitions. So here, this is a simple particle filter-based object detection systems. But once robot update, in order to calculate the particle filters or brief state of the object locations, that information is calculated in the or updated in the 3D space in the languages. And that 3D space is also directly used for the motion generation. So by using these systems, recognition part and motion generation part can be tightly connected within one systems, one languages. And this is another example that because of language based on the Lisp, our system is based on the Lisp languages, and Lisp is very good for the symbolic representation or reasoning. So we can connect that perception and the motion generation system with the high-level planning or task descriptions. So here is how we build the, how we describe the T-serving task like this. And I think this is a very simple classic AI example that if you have a different start state but share the same goals, you can generate the different type of the different sequence of the actions. And again, the system is written in our use Lisp systems. We can directly generate the motion of the robot like this. And we translate this information to the real robot. And also, what we are interested in the most verification systems. And the idea of this system comes from what we did with a small robot. In that robot, what we interested in is not walking, but how we can find the falling down and how we can wake up from that. And this is exactly, I think, the same idea. And the important thing of the action is not to execute perfectly, but to find the action is succeed or not. And the more important thing is how we can recover from that situations. So here we added in our high-level task planning systems, we look into the effects section of this action definitions, and these effect sections tell you about what can be expected, how can I say, sensory information after the robot execute actions. And by looking at these effects informations, then we can find if the action is succeed or not. So here is some example that robot try to generate a plan. So right side is a plan, and you see the red rectangle, and that goes from top and second one and third ones. So this is very simple plans, but each actions, and these rectangle shows each actions, but each action have a verification system that every time robot executes action, it checks if the action is succeed or not, and if the robot fail to execute action, then robot replan again. So this is how robot repeatedly try to grab the object, and finally robot is able to apply the tea from the bottle to cup successfully, like this. So this is, in this case, the action is very sequential version, but I think the interesting part here is, can we generate that kind of the state machine automatically or programmably? So this is another example that we are interested in, is we are trying to build a system that generates the state machine based behavior controller from high-level task description. And this is not so difficult because after we solve the put the goal to the high-level task description or task planning system, it can generate different type of the actions list, and this list can be expressed as a plan graph, and by merging each plan graph, we can generate the one big state machines. And what we interested in is, can we extend this system to failure recovery situations? So in order to do that, our solution here is to add the new information called effect fail. So we have to add the what can be expected situation after the failure. So we can understand if the action is succeed or not by looking at the effect, because if effect is not satisfied, something wrong. But the difficult part is there is many situations of failure cases, and in order to make the state machines like right hand, you need to know the next state after the failure. So in order to know that information, we need to add this effect fail information here. So by adding this information, we can generate this type of the state graphs from the PDDL action, the PDDL plan descriptions, and this robot behave based on this state machine, and we did not write this state machine because we only write the task description for the PDDL with the effect fail information, and this graph is generated automatically. So this is how we use the knowledge-based systems in our laboratory, and also how we integrate everything from perception, planning, and motions into one systems. And this is another topic that, because I think I heard there is a lot of students coming to this event, and I think what I always talk to students is imagine versus execute. And this is a quote by the Professor Kanade. This is, I think everyone knows, famous professor, robotics professor at the CMU. And he wrote more than 300 academic papers, but I think it's very hard to find his books because he did not like writing books, even if they are scientific books. But this is, I think, only one of 2 or 3 books he wrote. But unfortunately, this is in Japanese, and this is not a scientific book. It's just books for the businessman. This is, I don't know why, but it contains a very important message for the researchers, which is imagine like amateur and execute like expert. And this is very important because if you are, how can I say, undergraduate or students, usually you imagine like amateur and execute like amateurs, and that is normal. And if you are postdocs or professors, you imagine, I mean, think about the research plan or something like that, like expert, and execute like as an expert. So this is normal. But what he did is he always tried to imagine like amateurs and execute like expert. And this is very important. And if you remember his works, like he started the autonomous car in 40 years ago or so. He wanted to drive from West Coast to East Coast with drinking or reading books. So the motivation of that research is very amateur-like, but he uses his knowledge on the computer vision to execute, to build the autonomous cars. And what he said in this book, the worst case is imagine like expert and execute like amateur. So this is the worst case for the researchers. And if you look at the papers, a lot of paper uh, do such things. And so this is, I think, it's important, and the humanoid robot is a good tool for, following this code, because if you look at the robot, you have a lot of imaginations, and if you compare the robot with humans, you find a lot of difference, and these difference must be, gaps to be filled in, and this is the good research, I think. So what we by remembering the quote of Professor Kanade, one thing is we want to robot to behave naturally like humans, and I think the robot to find failure and replanning is also the same things, because human is not able to execute action in the 100%. And I think the usual people think the robot should perform the task in the 100%, but I think it is very difficult and sometimes impossible. So I think I came up with the idea from following this statement. And also this is another example of researches by Dr. Urata. And he wanted to build the robot that can keep balance after kicking. And the origin of this idea is very simple, because he liked to watch YouTubes, and he looked at a lot of the Boston Dynamics researches. And at that time, Boston Dynamics shows a big dog is a four-legged robot recovering from the human kicking. And he just simply want to make this happen with humanoid robot. So motivation is very simple, but he solved in very expert way. He built this robot, and also he built the motor driver of this robot by adding the water-cooled systems. And also he write his own balancing control systems, and also he implemented in the assembler to running this controller in the real times. So this is, I think, started with very simple motivations, and but he used his all of the talent to realize or achieve this result. And also this is another example, and this is example of the motion imitations from human to robot. And this is I think this is very typical example that you have a Kinect camera and observe the human motions, but because of that guy is a researcher student, and he's very good at dancing. He broadcasts his dancing online with YouTube, so he's a dancer. And he knows the important part of dancing, which is not just imitate the human motions, I mean the trajectory of the action, trajectory of the joint, but he knows the important part of the dancing is how foot is touched to the ground. So sometimes human touches the ground by toe or knee or something. So, and also he like animations. So this is, I think this, I had this very famous Japanese animation, and he looked at this YouTube video and dance like this, and captured by Kinect and transferred to the robot. So this is what he want to say, and he want to present in the conference. Of course, he didn't do that, because this anime is not so good, I think. And this is another example, and because of the one student want to play tennis with a robot, and I think most of the human robot motion is not so smooth like this, because if we decompose these motions into the component, I think what important thing is the speed of the hitting point. But if you play tennis, this is more important to draw back or something like that. And this is very interesting because if you use optimization techniques, by adding some constraint of the starting postures and the speed of the hitting point, then that optimization process automatically generates the drawback motions. But this is just the motions, and more important, more difficult part is how we connect to the vision systems. And this is still our ongoing project, that robot is not able to hit the balls because it's very difficult to combine the vision system as motion in the high speed. So another thing that I'm very interested in the perception side, and I started my research with vision systems, and the vision system can detect the object or environment situations, but if in your everyday activities, I think you can perceive more than that. For example, if you see the grass in the, very close to the edge, you feel like this is very dangerous situations. So you feel more than just detecting a classifying object from the visions. And also the physical property like the weight or friction is something that we want to measure. And the human can find this disk is heavier than chairs. But vision system cannot tell you that one. And one idea is, of course, user knowledge. And the other idea here is robot slightly move the object and they try to find the, how can I say, a hypothesis of the weight of the object. And if the hypothesis is correct, then robot execute the pre-planned motions. So here, robot slightly moves the object, and he finds the object is heavier than expected. So instead of lifting up or sliding, he executes this kind of the pivoting motions. And this is another example of understanding the physical property in the continuous space. So right side, this figure shows how robot belief state of the friction and also center of the mass. And this graph shows the red part is high probabilistics of the parameters. And after robot is moving the object, then it gradually finds the estimate the these physical properties. And this is another case of our APC, Amazon picking challenges tasks. And the task of this motion is named the store motions. And robot picks the object in the red box in the bottom and pick some object and put it into the shelf. And of course, robot is not able to execute this action with 100% success rate. Sometimes the robot falling down or partially, stored. And what we want to do is, can we understand if the action is failing before finally execute the actions? So just grab the object, and we want the robot to, how can I say, estimate if the action is going to success or not. So he did he take a lot of test data, about 300 trials, and after that he trains the images taken just after the robot picks the object. And this shows the green part, left top green part shows the robot tell you that, okay, you can continue executing action because the action has more likely to success. And right bottom shows the robot says, oh, you should stop motions because action is likely to fail. And in that case, robot uses the other hand to do the dual manipulations. So here, in the top, robot execute action with one hand, like this. Okay. No. Okay, so, and the bottom video shows the robot execute a task with one hand, and the top video shows a robot execute the task with a two hand, because a robot knows if you execute the task is just by one hand, it's likely to fail in top situations. So this is another example about contact or tactiles. And of course, for the manipulation, I think the contact or tactile is very important. But most of the contact or tactile sensors, you know the contact after touching. But once robot touches the object, it has more chance to break or move the object. So when we grab the object, mostly it's success or failure. And we want to avoid the failure situation before it's actually grabbed. And human can sometimes understand, you almost grab object, or the state of the contact is more like continuous, not the binaries, because of the softness of the fingers. So here we added the proximity sensors to detect the object before the context and use that information for the contact sensors. And here is some examples that using these grippers, you see some red or green, which shows that the contact sensor is activated. And here, robot goes through the bags, and you see something is some signals there. It shows that robot is close to the bag and try to move the position of the grippers. And also, robot feels something in the tip and opens the grippers and grabs this, I think it's a plastic bottles, is in the bag. Oh, it's a paper bag. Okay, so this is the last topics, and another our interested is how amateur will program robot. So assuming that if we have a robot in everywhere, meaning every house or everywhere, what kind of interface could be used for program the robot? Because one idea is build some complete machines or perfect machine, and robot, you don't have to program a robot. And the other idea is you have a very nice voice communication interfaces, or view-based imitation interface, so that you just tell your robot about new actions or new ideas, then you can tell your robot what to do. But another idea is we still need something to interact with robot, even if you have a robot in every homes. And here is one idea that AR-based whole body manipulations. So the guy in the back wears a VR glass, AR glass, and have some two devices and controls the robot. And difficult part of humanoid robot is you cannot, you just transfer the joint angle from human to robot is not sufficient, or just the position of the effector is not. Robot have to keep the balance in real time as maintaining the original intention of the humans. And this is another example of simple idea of using the multi-touch interface like iPad to communicate robot that where the object is and the name of the object. Okay. And this is another example, and the technology behind this is one student tried to transfer the program of the robot to the other robot. So here he first writes a program in PR2 using the Lisp languages, but he wanted to transfer to the robot as a different type of the robot. And his idea is very interesting because he did not transfer the language level, but he want to transfer the motions in the action or trajectory level. So the system observes the trajectories and try to build the flow diagram, and then create the languages can be applied for the different shapes of robot like this. And this system can be considered as once you have a motion of the robot, then you create the control flow like block 0 to block 5, and that can be transferred to the visual languages like this one. So here we are currently interested in the building some visual language for the robot like this, because if you take the underground metro in Tokyo, you see a lot of advertisement. It is saying that robot programming school for the junior high school or elderly students, because in Japan it is says that programming is a basic knowledge for the educations, and government try to teach the programming from the elementary schools, and the robot is a good example of that. So another possibility is in future, every kid can program. Like nowadays, everyone can calculate math, or even for example in Japan, everyone can write the Chinese character. Everyone can write a program as well, and they use that knowledge to program the robot. But I don't know this happens. So I think this is almost the end of my talk, and we have a different project in our laboratory. Here is another example. We try to build super complex robot like human bodies. This also started very simple idea that can we build a robot with a human? Can we build a robot which has something like human body and muscles? So now we put this robot into the small car and create some autonomous driving car using the robot. And also this is another interesting project. We try to build the flying robot that can manipulate. So this is multi-link flying robot. The left one is a two-dimensional versions, and the right side is a three-dimensional versions. And because of the robot can change its postures, we want to manipulate the environment. So in this case, what robot can do is just to move the, some panels like this and go through into it. And if you look at some errors, you see the errors. So this robot is very noisy. Okay. So this is conclusion of my talks. I presented our systems, knowledge representation systems, which is written in or implemented in the single-use Lisp environment. And I think this is very important to imagine like amateur and execute like an expert. And the humanoid robot or everyday activity is really the source of the good ideas. So you have a lot of imagination when you consider the everyday activities. And if we compare them, activities of the robot and activities of humans, and you find some gaps, then it must be filled in, and that should be a good ideas. So in our case, we are more interested in the human-like behavior, and also in perception part. I think nowadays perception is almost solved by the deep learning, but if you compare with the humans, I think there's more we can do, because we perceive or we understand not just a level of the object or scenes, but we understand more than that. And that information is which we use for everyday activities. So thank you very much.